My name is Konstantin Gulen. I'm a senior machine learning engineer here at Neural Magic. And today I'll be walking us through pruning and quantizing models without retraining. So the idea is we're going to walk through how to use these state-of-the-art algorithms, OBC and OBQ, to do one-shot compression of our already trained models. And before we dive into it, I also wanted to point out here in the bottom right, our GitHub, Twitter, and Slack. Especially encourage folks to join our Slack community. We have an active community of people working on different problems, and it's always interesting to see what you are working on and to help you in your sparsification journey. But before we dive into it, excuse me, I'm going to hand it over to Mark to tell you a bit about Sparsify.
Hi, everyone. Thanks, Konstantin. My name is Mark Kurtz. I direct the machine learning full stack teams here at Neural Magic, and just wanted to highlight something that we have coming out. We'll talk a little bit more about it at the end, but all the research that we've been going through in these lunch and learns and we're going through today will be available in our Sparsify Cloud product, which we're going to be launching as a beta and GA later this summer. And currently we have an alpha version that we're looking for testers on. So please definitely, if you're interested, check it out. It allows model optimization to be really easy, really quick, and puts a nice UI on top of it. So feel free to stick around towards the end. We'll dive in a little bit more into the feature set, and otherwise I will be here answering any questions that you guys have over Sparsify or over the research that Konstantin is going to be going through. Thanks, everyone. Back to you, Konstantin.
Thanks, Mark. Okay, so moving on to the agenda, let's talk a bit about what we're actually going to be covering today. So first, we're going to go over the background of pruning and quantization. We're going to talk about what is pruning, how can it be categorized into different categories, and what is quantization. And you might already be familiar with these compression methods, but hopefully this is a useful overview, and it'll get us on the same page in terms of the terminology that we use in the rest of the talk. Then we're going to set up the actual post-training compression problem, or one-shot, as we can also call it. And we're going to set it up in a technical way, and then we're going to talk about how OBC and OBQ provide solutions for this, for pruning and quantization in a very efficient manner. Then we're going to go over the part that actually matters. We're going to see how these results applied, or these rather methods applied to a CV and NLP applications, the kind of speed up you can get, and the accuracy that you can maintain from them as well. Then Mark is going to dive a little bit deeper into Sparsify and how you can apply a lot of these algorithms that we're developing with Sparsify. And then finally, we're going to open the floor for Q&A at the end. So let's get started by just going over what is pruning from a very high level. From like a 10,000-foot view, right? Pruning in an illustrated sense, essentially, what we're doing is we're just removing weights from a model in order to make it more lightweight and reduce the number of flops required. In this illustrated example on the left, you can see we have a simple fully connected network. On the left, it's fully dense. In adjacent layers, every node is connected to every other node. And then we prune it. We remove some of the connections, and we get this more sparse network, so that at least theoretically, right, the number of computations you have to do from input to output are significantly less. In reality, right, we're dealing with matrices as our weights. And so if you look at it in matrix form, we're essentially replacing real weights with zero weights to make them non-ops. And so, like I said, the main reason we do this is to speed up our models, and to do this in an intelligent way where we actually get to maintain our previous sense accuracy, so we can get faster models that perform as well as their bigger over-parameterized versions. And so pruning can be categorized by quite a few different ways. These are kind of the three main ones that will cover most pruning methods you're going to see. First, let's talk about the difference between training-aware and post-training. So in training-aware pruning, you're removing weights as you're training, and this allows the model to adapt to sparsity as it trains over epochs. So you can see in this sparsity graph, you can see like an example sparsity schedule you might use. So you're going to prune bit by bit, right? You're going to increase the sparsity level until finally you get to your target sparsity. And you'll notice the target sparsity doesn't happen at the end of training, because we want to give it some time, the model some time to adjust to the new sparsity and regain full accuracy. And so, yeah, we typically have some epochs of training afterwards as well. And so you can see in the accuracy plot, for example, that as we start pruning, accuracy is likely to drop, and then it's going to regain that accuracy through fine-tuning on the fully sparse model. This typically, the training-aware approach A lot of state-of-the-art methods tend to use this. It gives you pretty darn good results, but it can come at a pretty high cost. One of the biggest costs is that it requires training integration. So you need to integrate your pruning methods into your training script, which, if you vary across models, applications, tasks, etc., it's pretty hard to standardize. And it's one of the problems that, we solve here in Neural Magic with our tools. But then on the other side of things, we have post-training pruning or one-shot pruning. Now, this is much simpler. We apply it to already trained models. But, typically in life, there's no free lunch. So it's a simpler method, but also we have to pay a cost in terms of accuracy. And sometimes there's a calibration data set that's used. This does not involve any training. You basically just use the calibration data set to collect some statistics about your model and to figure out which weights you want to prune. So another category that's used to separate pruning methods is the mask type that you use. So if we have a weight matrix like this, we can impose some constraints on how we want to select the weights from the matrix. In the most unconstrained example, we have unstructured pruning, where essentially we're free to choose any weights based on our criteria. There's no real structure imposed. Semi-structured pruning imposes some structure, but not too much. For example, 4-block is an example of this, where instead of pruning singular weights, we choose blocks of 4 of weights to prune at a time. If you're familiar with the tensor RT24 pruning approach, this is another semi-structured approach where you prune 2 out of every 4 consecutive weights. Then on the other side of things, we have structured pruning, where you can prune whole columns, channels, or even layers at a time. And essentially, the trade-off between these is you're trading off, how good is your pruning method going to be? How much can it give you a speed up while maintaining your accuracy versus how easy is it to implement and run? Like with structured pruning, if we look at this example here, if we're simply to compress our matrix after getting rid of 2 columns, suddenly we have a 2x4 matrix. All math that's done with this layer that requires less flops. And so we don't need any special implementation, right? But this is also a very limited approach, because in most applications and most models, structured pruning can only get you so far. You can reduce some amount of flops, but it's pretty quickly your accuracy starts degrading. In unstructured pruning, you can prune, like a Neural Magic would prune up to 95%, some of our models, 95% and higher, and able to maintain baseline accuracy. So you're able to, reduce a lot of the flops theoretically, and then you have to be pretty clever about how do you get that inference speed up. And that's also part of what we do is, our implemented engine that does that. But yeah, this is kind of one of the categorizations. Then finally, we go to pruning criteria. So how do you actually choose which weights you're going to prune? In the simplest approach, we have 0 order methods. So just based on the magnitude of weights, like the base simplest case you can imagine is you look at your weights, you choose the ones that have the lowest magnitude, and you prune however many you need to get to target sparsity. So if it's 50%, then you remove the half of the weights that have the lowest magnitude. Then there's first order methods, which use the gradient of the loss. So movement pruning is one example of this. And then finally, we have second order methods. So this is based on the curvature of the loss. Obviously, as you go up in orders, you get a more accurate method, but also requires more computation or maybe more cleverness to get an optimal solution here. And so you might have got the last lunch and learn that my colleague Elder presented. That was in Woodfisher. That is also a second order method. Today we'll be covering OBC and OBQ. There's a few differences between them, but the main one is that Woodfisher was a training aware method, so it was done during training. And OBC and OBQ, which we'll be covering, is a one-shot method, so done on an already trained model. So also a quick quantization overview. So quantization just basically is converting your high precision weights, whether they're FP32 or FP16, to int8. And just like pruning, it can be done in a training aware or post-training method. And it can also be combined with pruning, and that's typically our best results combine both of these. So we prune a model to high sparsity and then try to quantize at the end in a lossless way. But okay, let's dive into the actual post-training compression problem and set up a problem we're trying to solve that we can then give the OBC and OBQ solution to. So, we start with an optimized layer and we have some inputs. Optimized layer, how do we get that? Well, that's what training does, right? When we have a trained model, then our layers are, at least hypothetically or theoretically, optimized or very close to optimal on the loss surface with respect to the inputs. So we're going to treat this on a layer by layer approach. So we're compressing each layer one by one independently. Although there's variations of this where we can actually take into account the interactions between layers as well. And so essentially our goal here is to find a set of compressed weights, we're going to call it W hat, that matches the performance of the original weights as closely as possible, while satisfying some, sparsity constraint. And so we can see this is essentially the phrasing of our problem in equation form, but really all this is saying is what the last two bullets show, and that's that we're trying to minimize some loss between our original layer and our sparse layer, and it's subject to some kind of constraint here, and the constraint is our compression constraint. So for example, maybe we want to sparsify up to 80%, or maybe we have a flop reduction target. This is essentially what that constraint means. And we're going to specifically focus on linear convolutional layers, which end up comprising, most of what the large modern models use anyway. And we're going to use squared loss. So that kind of compresses down the equation above. And to this, we just have the squared loss of the outputs between our layers, between our original dense layer and our compressed layer. So let's go into the OBS solution. So OBS is kind of the history that OBC and OBQ and a lot of these second order methods are based on. It's a seminal paper from 1993. Basically, it gave an exact solution to the second order neural network pruning problem. And essentially what it says is that if we have our second order information or our Hessian H, then we can figure out the best way to prune, the weight that we want to prune that's going to impact our loss the least, based on this equation here. So basically for each WP is like a weight in your weight matrix. And so if you calculate for each weight, the weight squared divided by, its diagonal entry in the inverse Hessian, and then you find the one with the lowest value, that's the one you want to prune. And what it gives us in addition to that is it gives us actually an update value as well. And so what that means is that when we prune a weight and we set it to 0, we also apply an update to the rest of the weights to accommodate the fact that we just pruned it to 0. So pruning a weight, moves us a little bit further away from the optimal spot in our loss surface. And then this update step basically kind of takes a step back towards our optimal spots so that we can maintain our optimal model and maintain our accuracy. So this is kind of the seminal paper that a lot of following second order work has been based on. And we get H by basically having a calibration data set. So this is where the one-shot or few-shot, compression comes in by using this calibration data set. We run it through and we get our estimated value of H and perform these steps. But let's see how well this actually scales. And that's where we're going to see the technical challenges of applying this paper from 30 years ago to modern problem sizes. So if we look at, a typical weight, and we're going to, by the way, compare this to a BERT-based example, we're looking at a single layer of BERT-base. This is just one sample layer, but, a simple layer might have on the order of about 1 million parameters. Then our Hessian is going to be D squared, where D is the full number of elements in the layer. So very quickly, we're already blowing up in terms of the number of elements that we need and the amount of memory and compute. We got 10 to the 12th just for the size of one Hessian here. Then the compute is D to the 4th. That's mainly driven by the fact that we have to do all these Hessian inversions along the way. And so you can see pretty quickly this blows up and it becomes unmanageable. Even in memory terms, we need an unreasonable amount of memory just to compress one single layer in modern models. So let's see how we can maybe come up with some tricks and make some observations in order to bring this computational complexity way down. So the question is, can we reduce the computational load? So first observation we can make is that the loss is independent in between rows, because the output of each row is independent from the output of another row, just based on the simple matrix multiplication math. So we can actually break this out into the sum and treat the loss of each row is an independent choice. And we'll see how that's going to come into play a little bit later. But one of the immediate effects we get out of that is, okay, we can also see that, solving for this, the Hessian is actually the same for all rows. Sorry, that's a typo. That's meant to be the Hessian is the same for all rows. And so we can reduce the size. This is the exact formula for what the Hessian is, but the size is now down to just the size of the column squared. So already a decent improvement in compute and memory there. Now, observation 2 is, as we're pruning our weights, we have to recompute the Hessian each time, right? Because if we remove a weight from a row, then we can remove the corresponding entry in the Hessians, or entries rather, and we get the corresponding Hessian, but then we can't do the same in the inverse. So we have to recalculate the inverse each time. And right, as I mentioned, this is the most computationally expensive part of this whole process, and kind of what drives the complexity cost here. And so one trick that we can do to get around this is use Gaussian elimination. So this is basically an exact, it is not approximation, it is an exact update step, which allows us to remove, do the corresponding removal of a weight in the inverse of the Hessian through this this step here. And this ends up being an OD column squared cost, so down by an order of 1. So this is a pretty significant driver in improving our efficiency and getting down to a speed where we can, again, manage these modern models like BERT and etc. So what we have now is that we have that rows are seemingly independent, right? But we still want a global pruning mask. If we look on the right here, imagine just this is like your weight matrix, the colors are maybe the magnitudes. But if you want 50% sparsity, you don't know how much is going to be pruned from each row, right? There might be a row that has all important weights and it might have 0 pruned from there. And there might be a row that has, weights that contribute very little to the actual performance, and you prune most of those or all of those. And so even though the error can be independent, the actual mask still kind of ties it as a global problem. So we can't quite break it down into this independent problem yet. But let's talk about what is actually independent for each row. So the order of pruning, right? If we know that we want to prune 5 weights from a row, then we simply follow the formula that was given to us by OBS and that update, and we do those 5 update steps. And that is going to be independent for each row. If you're pruning 5 from row 1, that's completely independent. That process is going to be completely independent of how you're pruning weights from the other rows. And the other thing that is independent between rows is the pruning updates. So the magnitude of the updates, right? We talked about delta P before, the update you make to all the weights when you prune a weight. This is also independent. So essentially what we see here is, if we know ahead of time how many elements we want to basically remove from each row, then we can essentially prune them all in parallel and get a significant speed up that way. And so the way we can do this is actually by first pruning each row independently to 100%. So if we know we're pruning to 100%, again, we have to fully parallelize this. We prune everything to 100%. And then by pruning it to 100%, we actually have a full database that we can then reference to reconstruct any sparsity level we want. And so let's take a look at this in kind of a more granular picture here, because I know that might have been a little confusing, and maybe we can take a look at an exact example here. But if this is our original weights, let's just look at one row at a time first. So this row has 3 weights, right? And you can tell this, maybe we can say that this is the weight that impacts the loss the least, this is the second, and this is the most important one. And so we want to prune it to 100%, right? Because we want to create that database. And so first we prune this one, and we have a corresponding update, and that update we're going to call a trace. And so for each update, each weight we prune, we have a full trace. So first we update this one, and we have a trace which updates the rest of the weights. So this is a 3-element trace. And so then we update this one, prune this one and do the same. And then we prune the middle one and do the same thing again. And so you can see here, we end up with this 3 by 3 pruning trace, which is essentially our database. Now, if I go back and I calculate the global mask, I know that, in this in this row, I want to prune just one weight, then I reference this pruning traces or the database, and I get the corresponding entry, and I just pull that into my new weights, and I do that for each row, and then I combine all of these, kind of sampled traces together, and then I have a fully compressed model. And kind of part of the beauty of this too is that once you have this fully pruned, 100% pruned database, you can actually reconstruct that layer at any sparsity level. Once it was like a very low computational cost. You have it there, you go back and you say, okay, 85% sparsity, didn't run as fast as I wanted it to, so I'm going to now bump it up to 90%. Then you go back and you reference the database, and you really have minimal computational cost at that point. And what's even better is you can actually plug it into some optimization algorithm where you can essentially, you can compute the sparsity for each layer at a number of different levels. And then you can have an optimization algorithm which figures out, based on your hardware, what level of sparsity to apply to each layer to achieve your target flop reduction. So this can be like a very powerful method for finding the optimal, even your sparsity profile can come, you can determine from applying this method. And also another step that I should mention is, how do you determine the global mask? Well, so with each of these steps, you also have the loss, right? And the loss, again, is that formula given to us by OBS. It's the WP, right? The quantity of the weight squared over the inverse of the corresponding, the entry of the corresponding inverse Hessian. And so we have these losses here, and we can reconstruct the mask, and this is how we know how much to prune per rub. So the main takeaway here is that we're parallelizing everything to a per row process, so that essentially we can take advantage of parallelization and get a much faster and feasible runtime here. And so you'll notice here it says less compute, right? This is actually the method that I talked about, is where we compute all the traces, and this takes us less compute, but it is a little bit memory intensive, right? Because you have these, you have to store all of these traces in memory, and this means like many copies of your weights. Whatever is the size of your weight matrix, you have to store multiple copies of it. A simpler approach, or sorry, not a simpler approach, but approach rather that uses less memory, is to not store the traces and instead only store the losses. And if you do that, actually, it's one of the things that the paper showed is you can reconstruct the perfect update by this equation right here, the group update equation. And in practice, this ends up being significantly faster than computing all the traces from scratch. So you have to do a little bit of extra compute, but it's not nearly as much as you originally had to, and you have a much smaller database. So, if on-disk memory is a constraint, then this is another alternate kind of version of this that you can do. And they're equivalent. One is not an approximation of another. They give you equivalent results. And so we can see basically this is what we get as our final basically complexity in terms of time and memory. On the time front, so remember each one of those Gaussian elimination steps takes d squared time, and then we have to do it for every single element. So, d squared is in d column squared, so number of columns squared. And then we have to do it for every element in the matrix, so we get d row times d to the column to the third, which is much better than the original O of d to the fourth, where d was, remember it was every element, so it's d row times d column. So significant reduction there. And then you can see the difference in memory between going with the less compute route or the less memory route. So again, kind of a trade-off you can do there. So we saw OBS being applied to unstructured pruning, but can we use a sparsity mask alongside this method that is maybe more semi-structured? And the answer is yes, we can. And it is actually simpler than we would expect. So for NM pruning mask, like the one used in TensorRT, it is relatively simple. Basically, instead of at each step choosing the weight that has the lowest, loss in the row, we look at it sections of, let's say for a 2-4 mask, we look at sections of 4 in the row, and then we just prune from there only up until each section has 2 taken from it. So this requires very minimal modifications to the algorithm. And then if we want to do block sparsity, essentially there's this derived group update rule that the team, that publishes paper derived as well. And this allows us to prune whole blocks at a time. So instead of pruning a single weight, we can prune whole blocks. So the whole process is the same. Now the process is exactly the same as it was for unstructured. It's just we plug in a different equation at this point, but everything else is similar. And I forgot to say for NM pruning, it's actually even simpler because you know ahead of time exactly what the sparsity of each layer is going to, or each row is going to be. If you're doing a 2-4 mask, each row is going to be 50% sparse. So actually at that point, you don't even need to create a trace database. You just go through the OBC steps until you get to 50% sparsity and you stop, and it even becomes easier computationally. Then can we apply like this kind of approach to quantization? And let's take kind of a step back and look actually at a more generic version of this, right? We're going back to the OBS update rule. And if we actually solve a more generic version of it, we can see that what we get as the equation for the best way to prune and the equation for the update to make comes out this way, where this function C is our compression function. So for pruning, for example, C would just map any float to 0. And so if we plug in the compression, the pruning function here, we'll notice right away we get back the original OBS formula, right? We get the WP squared over the H inverse entry, and then we get the same update rule we had before. We just get this down to 0. But that means we can basically plug in any reasonable compression function here and work with that instead. And so that also means we can plug in a function that maps a float value to its int 8 quantized equivalent. And then we get OBQ. So that is basically, that's all we need to go from OBC to OBQ. It is literally just a change of this equation, and now we're able to quantize the weights as well as prune. So actually we can do OBC, and then we run OBQ and get this result, and get both a pruned and a quantized model in one. And OBQ actually tends to be faster than OBC, mainly because just like we talked about the NM pruning mask, we know exactly what the sparsity is going to be, right? When we quantize layers to 100%. We don't quantize just some of the weights in there. We want to quantize all of the weights. So we just go to 100%. Again, no database needed, and we're done. So pretty efficient approach. And one of the other kind of benefits of this is that, basically, typically in quantization, you're quantizing, as I said, all the weights at once. Here, we're actually quantizing one at a time, which might seem a little bit strange at first, but actually this is a benefit because as we quantize each weight, then we're able to adjust the rest of the weights for the new quantized weight, and actually we're able to recover more accuracy this way. So that gives us an even greater accuracy boost than a lot of standard quantization techniques. And so yeah, that's all it takes for OBQ, except not quite. They also add like one more trick. And essentially there is this kind of scenario that can happen where if you have quantization outliers, they're going to contribute the most to the loss, right? Which means they're going to be last in order to get quantized. And so if you're quantizing them last, that means that your loss is going to change quite a bit, but there's no other weights left to adjust, right? Because all the other weights are quantized, they're frozen, they're locked in place, and essentially you just have to eat that loss. So the solution here is essentially find the quantization outliers, and you do it based on, maybe this is the standard formula used in the paper, where delta is the quantization step, right? So it's the quantization step in float that you have, and then if the quantization of any of those weights is greater than half of that, if the error in quantization is greater than half of that, then you move that weight to the front of the line and you quantize it first, so that when you do the weight update step, you're able to adjust all the other weights to account for it, and it's not such a big loss in quantizing those weights. And yeah, that's the quantization step size. Yeah, so that is what OBC and OBQ are. Again, OBQ, OBC, they follow the same base algorithm. OBQ just extends it to quantization, and then you wrap your you do the conversion to full int afterwards. It's basically, yeah, giving almost free.
Constantine,
Yes.
before you jump into results, we had a good question come in where they were wondering why the Hessian is the same for each row.
Yes, good question. So let's go back a few slides. Where was this? Yeah, right here. Okay, so the reason we can say that is, if we're talking about matrix multiplication, what are we doing? We're multiplying. If our input, our input is a matrix, our weights are a matrix, and we're doing column to row. So each row is gonna get each column of the input, right? It's gonna touch each column of the input, and it's gonna output its own entries at its own row. And so essentially, this is just a byproduct of matrix multiplication. Essentially, is the answer. The outcome of the row is going to be independent of the other rows, just based on the way we do matrix multiplication. Yeah, I hope that answers it. Okay, yeah, let's go back down to results. Okay, so results. First, looking at some results on BERT. So this was done, by the way, with an NM pruning mask and quantization. And so what we see here is its comparison against Addaprune, which is another state-of-the-art one-shot pruning method. And you can see here that OBS outperforms the current baseline, and it gets relatively close to the base dense performance. So dense here is basically what is the performance before we touched it, before we recompressed it. Then Addaprune, right, is another state-of-the-art method compared to OBS. Similar results for ResNet with different types of pruning masks. So we have 2.4 and 4.8. 4.8 is obviously going to do a little bit better because you have more flexibility, less constraints. But again, in each case, OBS gets you the best performance. Yeah, and so we can look at some more examples here. So here we do some mixed quantization plus 2.4 pruning. So mixed quantization means we quantize the different bitputs depending on the layer sensitivity. And yeah, we can see here that depending on how much you want to reduce our operations and how much we want to speed up our model, we can kind of tweak that. But again, yeah, it also depends on the size of the model as well. So you'll notice the larger the model is, the more kind of room you have. But yeah, it's kind of showing a trade-off of speed up versus maintaining accuracy. And this is a pretty important dial to turn in general in this kind of sparsification, pruning and quantization problems. So we see the same thing for yellow here, and then the same thing for BERT. And this is just kind of a general aggregate across different models that shows the trade-up here as well. And so this is like an actual, right, in the bottom, it's inference times speed up. So this is, or sorry, actually the bottom one is over ResNet 50, or section D is over ResNet 50, but it shows the actual inference speed up. So the speed up that was attained versus the theoretical reduction of the number of ops you have to do. And so there's the question of, especially if you're doing unstructured sparsity, how do you utilize that in order to get a speed up? I mentioned before that if you're doing unstructured, you have to be pretty clever, and that's a big part of what we do here at Neural Magic is solve that problem. And so we have an engine that does that. And so this is just kind of a quick show of what you can get when you sparsify when you do unstructured pruning on your model. This is an example of ResNet 50, and you can see here that if we prune a model as far as we can while maintaining 99% accuracy, we can actually, and also quantize it at the end, we can actually get this kind of speed up improvement when running through the deep sparse engine, which again takes advantage of that unstructured sparsity. Yeah, and so now I'm going to hand it off to Mark, who's going to talk more about Sparsify. That's coming this summer. It's a big project we're working on. But yeah, take it off, Mark.
Thanks, Konstantin. Yeah, so this summer we have our first ML as a service product coming out called Sparsify. There will be free options for community and researchers and just personal projects, things like that. The ultimate goal is that if you're worried about trying to deploy either on CPUs or make your deployments cheaper, more performant, or less energy consumption, then Sparsify is definitely the place to go. We're going to have a few different pathways built on top of everything we've been doing, all the research we've been doing, all of the code that we've been pushing out, the open source code, stuff like that, and productizing an easy to use UI on top of that. So it'll be able to do one shot or post training, pruning, and quantization. And kind of going off of what Constantine was just working through, all of it's productized, so it's really easy to use. And also a lot of testing went into it to harden these algorithms and then also significantly improve these algorithms. So we have one shot. We have training aware, where it'll automatically create a recipe for you, and you can see what the effect of that recipe is going to be before running the training schemes. And then additionally, sparse transfer, where you just give it a data set and it'll automatically fit a performant model to it. So a ton of options in there, a lot of flexibility, and a lot of ease of use that we're really, really excited to launch. So if you're interested in being a part of our alpha process or just joining the waitlist for it, as we push out more, we're looking for active users to give us feedback on it so that we're building everything that that you guys need. And yeah, very, very excited to be launching it. I think that's it on the Sparsify side. So then, Constantine, let's jump into questions.
Yes, sounds good. Let's do some Q&A.
All right. So we have, do these pruning methods scale linearly, or are there ranges of dimensions where you get dimension returns?
Good question. So they scale linearly. I'm assuming that this means in terms of the size of the layer. So it is not linear, right? As we mentioned before, it scales, for example, OBC scales in terms of, we had the equation before, right? It was O of D column times, or sorry, D row times D column to the third. So it does increase with size, but we found that we can, prune pretty large models like Bird and ResNet 50 in the matter of a couple hours. And we've also found optimized versions of this that can prune models as large as GPT in reasonable time. Yeah, hope that answers it. So, I mean, typically, yeah, it scales quickly, but still we're able to manage in reasonable time with modern models.
Yeah, definitely. And I'm going to put a little bit of a plug in here as well, which is we have our Sparse GPT webinar, which is going to be coming out in May. And Sparse GPT was specifically looking at approximations that you need to make for larger layer sizes in these large language models. So there are approximations that you can do to be able to improve the performance on these so that they do work for larger models. Then we have another question. How do you decide layer-wise optimal precision for OBQ?
Layer-wise optimal precision. I wonder if, do you mean in terms of, so OBQ was, you said OBQ mark or OBC? So
OBQ.
OBQ. Oh, okay, sure. Yeah, so that's a good question. I mean, typically, at least in Neuromagic, we target int8. We see the best trade-off there in terms of not losing any accuracy while getting a significant speed up. But typically, especially in research situations, you might push that further. We're also exploring pushing it further. The way that you determine it is, I mentioned earlier, right, is that I mentioned mostly for pruning is that you can create these different sparsity versions of each layer, and then you can feed it into an optimization algorithm, which chooses the optimal combination for you by running it benchmarks against hardware, or by doing some, approximations of a different kind. You can do something very similar with quantization, where you just change the precision to, you have multiple copies of different precision, and you find which one works best.
Yeah, definitely. And just adding on a little bit more, which is that the default for it, that's usually a safe default for OBQ is int8. Pretty much everything can go down to int8, and that's default to go through. And otherwise, if you're looking to go to further compression, which typically doesn't have a lot of hardware support unless you're doing really large models. So if you're doing really large models, then it can definitely come into effect on the weights, and you can start going through what Constantine was talking about in terms of optimizing for hardware versus loss. And then we have a quick question coming in for, are there any internship opportunities open? And if so, what would be the best way to reach out? I'll go ahead and take that one. Currently for this summer, we do not. But if you're interested in either during next spring or next summer, feel free to connect with me on LinkedIn and also apply through the ML engineering or ML research positions on our jobs page, and just tag in their internship. And generally, we do a search across those to pull out any potential interns that we can bring in. All right, another one coming in. Normally, we expect that unstructured sparsity can only provide inference speedup if the underlying hardware can leverage the zeros and weights. Does deep sparse achieve this using only software?
Great question. Yes, so that is essentially the whole purpose and kind of bread and butter of deep sparse. It targets CPUs, first of all. So that's an important aspect of this, is that you're able to leverage that unstructured sparsity really well in CPUs. That is a solution that we found. And yeah, so deep sparse is a software-only solution. It currently it works on all x86 CPUs, but also we're currently targeting ARM, and that's already underway. We have support, for example, or at least experimental support for Mac OS that we're going to be releasing soon. And Mark, I'm not sure if you know the exact timeline, but we're planning to have full support sometime in the near future, right?
Yes, correct.
Yeah, good question.
I should note that, well, for macOS, if you use currently Linux, or sorry, not Linux, use a Linux container through Docker, it'll actually run on the x86 chipsets. For the ARM chipsets, that's coming up in the future for the M1 and 2. All right, and then we have another question. When putting it all together, in quotes, can you explain again the process for one row for an example, and also how the global mask was constructed?
Yeah, sure. I think it would be best to go back to the visual example. At least I'm a visual learner, so I feel like that's the easiest way to kind of understand this. But yeah, if we go back here and if we look at, for example, this top row of weights, right? So again, we have just 3 weights, and we want to prune it to completion. So the thing is, the first step is always prune to 100%. There is no mask, or rather the global mask is 100% for everything, or prune every weight. And so this is how we construct these pruning traces, right? We can also just construct the loss, but let's just stick to this less compute method, and then we compute all these traces. Then we also compute losses alongside it, right? So then at the end of the process, once we prune everything to 100%, we have this matrix of losses that is the same size, right, as our weight matrix, and we get the mask from there. So if we want to, for example, prune 50% of the weights from the layer, we look at our losses and we choose the weights that correspond to the 50% lowest loss changes. So the 50% of weights that contribute the least to the loss change as calculated by us here. And once we have those, then we can use that to reference their respective updates here in the traces and compose that back together. So the idea is basically, again, from the top, is we prune to 100%, then we use the loss to determine the global mask. And then from that global mask, we sample from the traces and basically kind of restitch, it's like we're taking pieces from here, and like restitch the full pruned layer, the prune matrix that way. Yeah, I hope that made it a little bit clearer.
And then another question, how long does it take to compress the models?
Great question. So, as someone asked earlier, how does it scale? And again, it scales pretty quickly with model size. It depends a lot on the model size and, of course, on your hardware. I've done some experiments. I've had to do some of this personally, and I've found that it takes about a couple hours, maybe for like a ResNet 50, for example. I think that's a pretty classic example. Yeah, let's say 2-ish hours for something the size of a ResNet 50 on about maybe a couple modern GPUs from the last couple of years.
We have another one coming in. It says, often we would like to fine-tune BERT models. Do you know whether this process still works well with a pruned BERT? And maybe same question with the pre-trained ResNet 50 that we want to fine-tune on a different data set.
Yeah, so the if I understood the question correctly, at least, the nice thing about one shot is that it's kind of independent of fine tuning, right? Like training aware methods are good for fine tuning, and that's what we typically tend to use. But in this case, you can fine tune your model and then you apply one shot at the end to your already trained models. So they should be independent processes. And yeah, we've done fine tuning on different tasks, and we've done one shot on those, and we find that it works well. So maybe the question was more about whether this works on models that are not the general just upstream models, and the answer is yes, from our experience, definitely.
Yeah, and expanding on that a little bit more, generally whenever we're fine-tuning the data set, fine-tuning to a data set, the data problems are going to be a little bit simpler than the upstream ones, right? So for example, for SNAP 50, and we're looking at 1,000 classes across ImageNet. Generally, everyone doesn't need to classify 20 different classes of dogs, and they can simplify that. And that usually means that you can actually prune a little bit more on those fine-tuned data sets. The other thing to call out is if you are just fine-tuning BERT and ResNet 50 and models like that onto your own data set, definitely check out the Sparsu. We have sparse transfer instructions. You can plug in essentially models that we've already done training aware sparsification on. And those will fine tune just the same as what you're doing for the dense model. So you can plug those in one for one. And then we have one more question coming in. How good are compression returns from OBQ plus OBC for lightweight models like MobileNet or Efficient?
That's a great question. It's not okay. So, I mean, I'll say first, we have not, at least I personally have not seen results on MobileNet, but I know in general that we use training aware compression, for example, MobileNet, and we see good returns there. We're able to compress it quite a bit. Only Mark knows the numbers. The pros have better than I do, but it's also on our Sparsu. You can check it out there. But the answer is yes, you can still get quite a bit of compression there, believe it or not. Even models like MobileNet are over-parameterized. And a large reason for that is that MobileNet is right. It's like you can kind of consider it as a realm of structured pruning where you remove layers and you choose simpler architectural choices. But again, structured pruning can only get you so far because of the constraints placed there. So we're able to, with unstructured pruning, take away more of the layers, more of the weights, and get more of a speed up there.
Yep, definitely. And so looking for OBC, we haven't done much, as Constantine said, on MobileNet and Efficient Nets. As you said, those architectures are already structurally pruned. But for quantization, we have done a little bit on Efficient Nets, and it works out very well. The other anecdote that I have is, at least for we've been working a lot on YOLO V5 and YOLO V8 models, and OBQ actually performs much better in the one-shot setting than quantization work training. So a little bit surprising in that aspect, but yeah, the algorithms are very robust and work generally across domains and architectures. So definitely try it out if you're interested. And then we have one more, which is, have you also worked on techniques for activation sparsity?
Good question. I think I might hand this one off to you, Mark, because I'm not as in tune there.
Yeah, definitely. Activation sparsity we haven't done much with it lately, and that's specifically because most of the newer networks have moved away from the ReLU activations, which we need for sparsity in general. They're moving to Swish and GELU and stuff like that. So there isn't much activation sparsity in a lot of the modern networks. But I think 3 years ago, we actually had a paper that was published in CVPR, which looked specifically at activation sparsity and if we could increase that for SNAP50, for example, and a few other models. And we did see really promising results on that. We were able to get above a 2x speedup just utilizing activation sparsity. I think we were increasing on average the sparsity across the entire model, or the activation sparsity across the entire model. Usually the baseline was around 40 to 50%. We increased it upwards to 70, 80%, and we're able to get a 2x on top of that. So yes, I can definitely point you towards that paper. Just give me one sec to pull it up. But yeah, technically it is still supported in the engine in deep sparse or activation sparsity. It's just typically that the combination of pruning, the weights, and quantization end up giving us better performance overall. But I am digging up that paper right now. I don't know. Let's see. We don't have any others coming in, so we have just a little bit of an awkward lull as I try and do this up. But Constantine, anything else that you want to add in for the talk?
Can't think of too much. I feel like we had some really good questions. It was nice to expand, to be able to expand on the things that maybe I could have spent a little more time on earlier. But yeah, no, I don't think there's too much I can add at this point.
Great. And I just linked that into the webinar chat for the activation sparsity paper. Oh, and then we have one more that just came in. Are you also looking into efficient training using sparsity and low precision?
Yes, yes. So I'm assuming this question is about basically accelerating the training process rather than just inference. This is definitely a new frontier in the industry in general, and for us, and the research team that we work closely with that also produces these results that we're sharing here. They have developed some methods, and it's something that we're looking at over the horizon, but maybe is not something that's going to be out in the near short term. But looks like there's some promising, definitely some promising work there to be explored further.
Well, one that we do have on sports training is the AC/DC paper, but that's not which I think we actually have. We had a earlier webinar on that one. We grab the AC/DC paper, but otherwise we can follow up with the sports training paper.
Yes, definitely. Good question, by the way.
There is the AC/DC. Oh, perfect. Thank you, Elder. Missed that. It's sparse prop.
Sparse prop. That's right.
Yeah, let me just grab the link for that one.
Elder is one of the authors of that paper.
Great. Well, I think that's everything then, and we're about time. So, yeah, thank you everyone for joining in. Thank you, Constantine. Great talk. And yeah, we will share out the other reporting and the links after this.
Thanks, everyone.